Welcome. This presentation is about Chapter 10 of the International Levy Handbook. Chapter 10 is about the construction of levies, and this presentation will be given by the two chapter leads of this chapter. My name is Charlotte Spitov, and I will present for you first the first half of this presentation, and Joe Forbes will present the second half. During the development of the International Levy Handbook, I used to work for Grondmei in the Netherlands and are now working for Royal Haskoning DHV in Australia. Joe Forbes works for the US Army Corps of Engineers in California. In this presentation we will give you an overview of the content of Chapter 10 and give examples of international good and bad practices in levy construction. Chapter 10 is the last chapter of the International Levy Handbook and describes the organizational and practical aspects of levy construction, identifying key constraints from environment, ground and hydraulic conditions. Key inputs from other chapters are from Chapter 7, Site Characterization and Data Requirements, and Chapter 9, Design Requirements for Construction. Key outputs of Chapter 10 to other chapters are on constructability of design for Chapter 9, and data related to construction as discussed in Chapters 4, 5, 6 and 9. Whilst Chapter 10 deals with construction, its target readership is primarily the levy owner or managers and the designers. The objective being to highlight construction issues that need to be considered in a day-to-day operation and maintenance activities and as part of the design process. I would also like to note that the term constructor is used instead of contractor to avoid describing the construction stages only in the context of a traditional contract. Although contractor is more commonly used, constructor can be used in every situation. In a similar fashion, designer is used instead of engineer. Chapter 10 is divided in 5 sections. The first section is on the organization of the construction process. 10.2 describes allowing for hydro-meteorological conditions. 10.3 is on setting up and managing the site. 10.4 fundamentals of earth construction, and finally the methods of earth construction are described. Section 10.1 first sets out the context of the construction to give a clear understanding of procurement approaches, inputs from various design stages and legal responsibilities. It then gives details related to planning the project and managing the risk to the construction program. And finally, it introduces the framework to ensure quality, occupational health and safety, environmental management, and data acquisition and management. 10.1 includes advice on the development of a realistic construction budget. The most reliable way of developing a realistic construction budget for any flood elevation project is to fully resource the developed construction program. Generic schedule of rate budgeting is unlikely to provide meaningful information. This figure illustrates the process for arriving at a program-based cost. The first step is to establish costs for the actual resources, duration and quantities from a resources program. The second step is to base the site overhead costs, sometimes referred to as the preliminaries, on actual forecast resources and duration. Step 3 is to assess the residual design risk and construction risks and appropriate allowances established. And following is to include realistic constructors' overhead profit risk and include allowances for escalation. This section also describes key steps in planning levy construction works. Key steps in these works are project-specific program constraints, checking the constructability, developing the methods, resources, and corresponding construction outputs, and defining associated costs. Other examples on how to best manage typical levee construction risks, quality, health and safety, environment, and construction data are also described in section 10.1. Section 10.2 talks about allowing for hydrometeorological conditions in the coastal and fluvial environment. This section describes how these conditions can restrict work by affecting operations and how they can create a risk of flooding, both to the construction site and the levied area. The second half of this section gives examples on how to limit flood risk during construction. This picture shows an example of temporary flood protection built to protect the nearby community during reconstruction of an existing flood protection. When working in coastal and fluvial environments, it is important to plan for hydrometeorological conditions because of the variability and severity of the conditions that could potentially rise, because of the risk of loss and damage, and because of associated delays, costs, and impacts if contingencies are not in place. This section describes the hydrometeorological issues for earthen constructions and gives examples of good international practice. An excerpt of this table with these examples is shown on this slide. In section 10.2.2, two main considerations are addressed. Hydrometeorological conditions may lead to flooding of the construction site and damaging the partly completed works, construction plant and equipment. And the construction site and activities may temporarily increase the flood risk in the levied area by increasing hydraulic loads or decreasing the levee strength. For example, by removing the revetment or digging in the levee, for example for a drainage feature or culvert, etc. Some specific good practices to flood risk management during construction of levees include the evaluation by hydraulic engineers of floodwaters and wave data for the area and generation of long-term climate predictions. Other examples are the investigation of water releases from upstream hydraulic installations and careful programming and stages execution to minimize impact on hydraulic regime. In a riverine environment, it includes the need to work from upstream to downstream to ensure provision of superiority of structures and upstream embankment protection. Other good practices are simultaneous advancement of protection on opposite sides of the river course and temporary measures such as bypass channels, temporary flood protection and or drainage ditches. I would now like to give the word to Joe Forbes, who will continue with this presentation. Joe, go ahead.
Thank you, Charlotte. Section 10.3 provides information necessary for setting up and managing the site. This includes many considerations that will affect the program at the stage of its definition, as well as during the construction. This section has three main subsections where a safe and environmentally friendly approach is presented for site management. In the first subsection, titled Managing Constraints from Natural and Human Environment, particulars of the site are considered. In the next subsection, access routes and traffic, access routes are described, and site traffic management and alternative delivery methods are presented. In the last subsection, managing archaeological remains and utilities, good practices for archaeological and utility-related issues are explained in more detail. In section 10.3, several examples of the types of construction constraints related to site setup and management are shown. One example is presented as a separate text box that contains a few descriptions of instances where constructors lacking environmental permits must face financial or even criminal consequences. Another example is a 2-page spread of a seasonal considerations calendar for protected species in the United Kingdom. The calendar is broken down into animal species with corresponding legislation, statutory authority, and requirements, and for each species it shows what type of construction activities would or would not be appropriate during each month. A third example, shown here by figure 1016, is a photo of excavation near a levee that contains archaeological artifacts. In this case, the artifacts are remnants of a historical city wall in the Netherlands. Section 10.4 focuses on the specifics of earth material works. The availability of materials is covered in the first subsection. Material availability is a primary factor in the success of a project. Preliminary design efforts can be very limited in scope, leaving the responsibility to the construction management and constructor to clearly identify sufficient accessible borrow material to complete the project. This may require additional sampling and analyses. The suitability of materials is covered in the second subsection. It's important to note here that material suitability may primarily be based on compliance with soil classification characteristics or index properties, which is described in more detail in Chapter 7 and Chapter 9 of the International Levee Handbook. Soil testing and the corresponding corrective actions play an important role in determining suitability. Shown here is an excerpt from a table that compiles the various sampling and testing required for levee construction. In this table, each type of test is linked to the corresponding section in Chapter 7 that describes it in more detail. Elementary operations and equipment use are covered in the third subsection. This subsection lists and describes common types of construction equipment used in the various steps of levee construction, including information on typical capacities and advantages and disadvantages of each equipment type. Though the types of operations and equipment used in levee construction are commonly found in other civil works, special considerations must be given to hydraulic environments and how the desired permeability and stability of the embankment can be achieved. The equipment used for levee construction falls into 5 basic categories. The first is clearing and grubbing existing trees and vegetation and establishing vegetative cover. The second is stripping and excavating, placing and spreading. The third is loading and hauling. The fourth is compacting the soil. And the fifth is treating the soil and installing sheet piling or cutoff walls. For each of the 5 operation categories, a table is included that describes for each equipment type the uses in levee construction, the advantages and disadvantages using the equipment presents, remarks or notes to further describe aspects of the equipment rating such as typical sizes and power output, and a photo of the equipment. Shown here is an excerpt from Table 1026, Properties of Equipment for In-Situ Soil Treatment and Installation of Piles. You can see that this portion of the table describes the uses, advantages and disadvantages, remarks, and rating for disc harrows and plows. Following the discussion of various earthwork aspects in Section 10.4, Section 10.5 focuses on the methods of construction at full scale. The topics on levee construction included in the section are the construction of levee test sections, the stages of construction, the differences between new build, repair, adaptation, and decommissioning works, monitoring of levee construction, the integration of non-earthwork features into levees, and construction approaches to repair pipes and culverts. On this slide is figure 1026 from the second subsection titled Stages of Levee Construction. This figure shows the steps involved in typical earthen levee construction. These construction steps are discussed further for a new build levee, but many of the steps can apply for levee adaptation and levee repair. Step 1 is site clearance, which involves the cutting of woody vegetation and large brush from within the levee footprint. Step 2 is topsoil removal or stripping, which is the removal of organic soil layers from the previously cleared and grubbed levee footprint. Step 3 is excavation of earth and rock materials, which is performed to remove wet, weak, or otherwise unsuitable materials from the levee foundation, shape the existing topography, provide for the installation of utility and drainage lines, or generate borrow materials for use in construction of the embankment. Step 4 is embankment filling, which involves the controlled deposition, spreading, and compaction of earth and rock fill materials to the extent required by the plans and specifications for the levee. Step 5 is topsoiling and vegetation, which involves the deposition and spreading of a layer of organic soils, some of which may have been generated from the stripping operations, on the exposed levee slope for the purpose of sowing, generating, and supporting a stand of grass. The last step, step 6, is revetment, which is normally composed of stone riprap placed on areas where the flowing water or wave runup might erode earthen embankments. As I mentioned earlier, there are 4 main types of levee construction. The first type is new build. The primary objective in new build construction is to execute the work in a cost and time-efficient manner to provide flood risk reduction while maintaining environmental safeguards. There is an example of new build construction on the following slide. During levee repair, the primary objective is to raise or strengthen the existing levee sections and elements without reducing the levels of protection or increasing the flood risk in an unacceptable way during construction. For the third type of levee construction, adaptation, restoring previously existing levels of protection and preventing further damage to the levee are the most important. And for the decommissioning of a levee, the key is to remove the designated levee features or segments to the designed levels in a uniform manner while preserving adjacent features and levels of protection. Throughout the International Levee Handbook, detailed examples used to illustrate certain principles from the main text are shown in example boxes. This allows an example or case study to be described thoroughly without cluttering up the main text. The figures shown on this slide are from an example box describing a new build construction project in Arles, France. A new protection levee was built in the northern part of the city to protect the urban areas from floods. It was made with impervious backfill and took into account various constraints related to the site, such as compressible ground, interface with the surrounding embankment structures, and several road and rail crossings going through the levee. The construction of the new levee included several phases. Phases 1 and 2 involved preparation of the project area through site clearance and topsoil removal, shown here in Figure 1029A. Phase 3 consisted of excavation of drainage ditches and an anchor trench, shown in Figures 1029B and 1029C. Figure 1030 shows Phase 4, where construction of the impermeable embankment was performed. Finalization of the embankment and installation of a protection grid occurred in Phase 5, which can be seen in Figure 1031. The project was then completed after the embankments were covered with topsoil, hydro-seeding was performed, maintenance and access roads were created, and security equipment was installed. This subsection in Chapter 10 includes the following primary objectives when integrating non-earthwork features into levees: maintaining continuity of defenses, maintaining operation of the non-earthwork facility, and ensuring good compaction to achieve a good seal around non-earthwork features. It also includes examples of the features and related good construction practices. This subsection is also a good example of the relationships and cross-referencing between chapters of the International Levee Handbook. There is a section in Chapter 3 that describes the definition, function, issues, and typical sketches for each type of non-earthwork feature. For example, Figure 1067 from Chapter 10 shows the foundation being constructed for a closure structure. Chapter 3 explains what a closure structure is and how it performs. The cross-links that exist between the chapters of the International Levee Handbook are crucial in the cohesiveness of the handbook. The last subsection of Section 10.5 discusses in detail the two most commonly used construction approaches to repair pipes and culverts through levees. Open-cut pipe replacement involves excavating down through the levee to the pipe or culvert, repairing or replacing the damaged elements, and then reinstating the levee. It is the most intrusive way to rehabilitate a failing pipe system. Slip lining is a trenchless method in which a liner pipe is installed inside of a larger deteriorated host pipe. This approach may be used where the deteriorated host pipe generally retains its original internal geometry. Shown here is a photo of segmental slip lining installation. A comprehensive list of these features can be found in Chapter 3. The issues, methods, and examples of detailed design are the same as for new pipes, which can be found in Chapter 9. Thank you for listening to this presentation. I hope it has given you a flavor of the coverage of Chapter 10 and encourages you to investigate the other chapters of the International Levee Handbook, which each have similar presentations. The complete handbook can be downloaded from the CIRIA website, the link to which is given on the current slide.